In between, if I am not audible, please let me know. Yeah, in this lecture, we will see the analog electronics basics. Those are digital circuits, rectifiers, and also we will see some of the basics of network analysis. So basically, the very important thing for very basic parts for the network analysis is branch, node, and loop. So if you see, if you take the circuit here, so can you tell me how many branches and how many nodes and loops were there here? If you are recall from the past knowledge what you have.
8 nodes, sir.
8 nodes. That only. The thing is,
Two notes, sir.
already whatever you know is the connection of two or more. Two or more. You see, two or more branches is a node. But generally, we will consider three branch connections, and that too if the there is no much there is no difference is voltage difference is there from one node to another, so all the nodes will consider as a one only. So going with that, so this is one node, this is B is second node, and C is 3 nodes. So in this circuit, even though 8 nodes were there as per the definition, but when we are solving the problems, we will consider only 3 nodes, assuming that if the all those nodes are at same potential. See, these all 3 nodes I am considering it as a one node because all these three are at equipotential only. So if the nodes are at equipotential, we will consider those nodes as a one node only. So same way below also. So generally the whatever the node is there below, that will generally consider it as a ground. And obviously by seeing this circuit we can see there are 3 loops for there, that is this is one loop, and this is second loop, and this is third loop. So but very important point, remember when you are talking about loop, always you will start from the node, you will start from the ground, sorry, you will start from the ground, and you will again come back to the ground. So then that only we are calling it as a loop. So this concept will help you a lot when you are solving the problems. So remember that when you are seeing as loop, you will always start from the ground and reach the ground back. So that we will call it as a loop. So totally here in this, how many branches were there in this? How many branches? This is 1, 2, 3, 4, and 5. So branches were 5, nodes were 3, loops also 3. And just brief it out what you already know. If you see whether it is network analysis or analog electronics, basically the elements were classified as two, right? One is active elements and one is passive element. So on what basis we will say that that is active or passive? On what basis we will say that particular element is active? If that element can able to deliver energy for infinite amount of time, then that particular element we can call it as a active element. So examples were voltage source and current source, right? And any other examples for active elements? Any other examples? Let's make this discussion interactive. So you already seen some active components or listened some active components in the past in your past discussions, right? Of your BTech. Yeah. What about transistor? That is BJT. BJT. and op amp. So not only it is delivering, not only it is delivering either voltage or current for infinite amount of time, if the particular element will have the amplification. So this is alternative definition. So if the particular element can able to do the amplification of the applied input signal, then that element also we can call it as a active element. So BJT means all the transistors, I can say transistors and op amp. So this can able to amplify the signal. So this is the alternative definition for active element. And see, these are independent. Whatever you're saying it as voltage source and current source, all these are independent sources. Whereas these are dependent sources. Whereas these are dependent sources. So these are coming under dependent sources. So independent sources, there are ideal or there, practical were there. Ideal means we have some particular element, ideal characteristics which we are not able to achieve, ideal values. So with the help of practical components, we'll try to achieve those ideal characteristics, right? So we have voltage source and current source. Same way practical also there. Only thing is for ideal voltage source and practical voltage source, what is the difference? You will have some source resistance will be there. Source resistance RS will be there in a practical voltage source. Same way dependent source, you know, right? Dependent source we will represent with this symbol. And if it is voltage controlled voltage source means this is voltage source. The control variable for this will be voltage. So like that, current controlled voltage source, current controlled. So here this is voltage controlled current source. Okay, so those are active elements. Regarding active elements, the same way passive elements, if it is not able to, same way if it is not able to, if the particular element not able to deliver the energy for infinite amount of time, so that element we are calling it as a passive element. So you may ask sir, the inductance and the capacitance can able to store the energy for some amount of time, and after the applied source near the inductor and capacitor, if we remove, we can able to deliver some energy. But the magnetic energy delivered by the inductor and the electric energy delivered by the capacitor is for a shorter amount of time. It's not for infinite amount of time. After some time, the entire energy there in these two components will be dissipated. So the capacitors and inductors will able to deliver the energy for a shorter period of time. So that's why we are calling this L, C and R as a passive elements. So there are linear, non-linear, linear and non-linear, all will be there. So these are some classification about what are the elements we will use in this subject. We'll try to revise the basic theorems of network analysis. So same, the circuit is given. For this, you just identify how many branches were there, how many nodes were there, and how many loops were there. How many branches were there here for this circuitry? Take the help of the circuit and try to tell how many branches. 1, 2, 3, 4, right? 4 branches. How many nodes? It's clearly visible here. 1, 2, 3 nodes. And just tell me this which one is parallel here? 10 volts and 6 ohm. These two are series or parallel, or else 6 ohm and 2 ohm.
Parallel, sir.
Yeah,
Parallel.
So these two are parallel, right? These two are parallel. So entire this group will be from these two nodes will be in series with 5 ohm and 10 volts, right? At these points, both the 6 ohms and 2 ohm were in series. Am I audible now?
Yes, sir.
So total number of nodes and branches were 4 and 3, and like that the series and parallel. Same, can you tell me now for this how many branches and how many nodes?
5 branches.
Yeah, 5 branches. Nodes. So
5 nodes.
this is 1, this is 2, this is 3, 3. And parallel series, anyhow you understood. So 1 ohm, 2 ohm are in parallel, 10 volts and 4 ohm are in parallel. So entire this and this and means will be in series, right? So Kirchhoff laws, there are KVL and KCL, right? The main Kirchhoff laws, KVL and KCL. Kirchhoff voltage law says, in summary, the algebraic sum of voltages there in the loop is equal to 0. In simple terms, the KVL says the algebraic sum of voltages there in a loop is 0. If you write in the mathematical expression, so sigma m equal to 1 to m, Vm equal to 0, where m is the number of voltages there in the loop and Vm is the mth voltage. So in the loop, if m voltages were there, the mth voltage is Vm is the mth voltage. Let's say means you see in this how many voltages are there? Always 1, 2, 3, 4, 5. 5 voltages were there. So m is m equal to 5. And Ohm's law. Well, this is correct. Whatever the Ohm's law I am showing here, will it be V proportional to I or I proportional to V? Any idea?
Both are same, no, sir.
See. The mathematics you see here, V is proportional to I means which one is independent here? I is independent here. If current is there, then only voltage will be there. But here I is proportional to V means if voltage is there, then only current will be there. Means in equation 1, current is independent. In equation 2, voltage is independent. How come you say both equations are same? If you remove the proportionality constant, V equal to proportionality constant is IR. The thing is, the final equations whatever got is same, but the concept behind is different. So anyhow, in a circuitry, if both were possible only, in order to confuse later people may ask you like if current is there, then only the voltage will be there. No, E- even in a circuit, voltage is there, current is also possible. Both the ohms, these laws were possible. Both were holds good. So here want to remove proportionality constant, you will get GV, where G is the conductance of the material. G equal to 1 by R. Okay. So these are the two forms. Still, there are so many forms of Ohm's laws are there. Almost 8 different forms of Ohm's law are there. Those were they need to be discussed in electromagnetic theory. But anyhow, for our network analysis, this V equal to IR is more than sufficient enough. So Kirchhoff current law says the algebraic sum of currents entering the node, algebraic sum of currents entering a node is 0. Or this can be told in reverse also, right? The algebraic sum of currents leaving also you can say. Any one only you consider. Where n is the number of branch currents, and nth n is the nth current, in is the nth current entering the node. So if we consider this is node n, so how can I write KCL for this? I will follow sum of leaving currents equal to 0. Sum of leaving currents equal to you also consider any one only. Don't consider both. Later the equations becomes wrong. Sum of leaving currents equal to 0. So based on that, can you tell me the equation for this? You will write like this. Sum of leaving currents, right? I1 is entering current, I2 is leaving current, I3 is entering current, I4 is entering current, I5 is leaving current. So if it is entering current, you will write minus I1 for leaving current, right? I am considering sum of leaving currents, but here I1 is the entering current, so I will write minus I1 for that. Same way I2 plus I2 algebraic sum, right? Minus I3 minus I4 plus I5 equal to 0. Like this, you will write the KCL equation at a node, right? You got right. KVL in a loop, KCL at a node. So we'll try all these network basics I need when you're discussing the analog electronics problems. So that's why I'm discussing all this now. So for the circuit below, find the V1 and V2. How will find? Simply if you find what is the current there in the circuitry I, and you can able to find easily V1 and V2, right? I will find out now. So 20. I will apply here now KVL, algebraic sum of voltages, right? So when you are applying KVL, you consider in this current direction flow any one sign, either the first sign. You see the 20 voltage source, this is plus and minus like this, right? Either you consider first sign of all the voltages or second sign of the all the voltages there in the loop. So I will usually consider the second sign. So second sign of 20 volts, and same way second sign of V1, second sign in this current direction, second sign of V2 is this. So based on that, if I write the KVL equation for this, 20 minus V1 plus V2 equal to 0, right? So how can I write V1? If this is I write, how can I write V1? Can you tell me based on Ohm's law V1 equation? based on Ohm's law?
So 2 into I.
Yeah, 2I. Based on Ohm's law, V2 equal to 3I. Right? So substituting these two in this equation, 20 minus 2I plus 3I equal to 0. So I equal to minus 20, right? I equal to minus 20. So V1 equal to minus 40. It is asked here that the polarities were they given differently, but when we are writing in the current direction only, so wherever current entering, there plus, wherever current leaving, there minus we will do. So as per your concepts, we will follow. Later we will find out V2. So wherever current entering is there plus, wherever current leaving is there minus, accordingly. So this will be, or this will also, you will get minus. So 20 minus V1 minus V2 equal to 0. So obviously 20 by 5 is 4 you will get. So V1 equal to 8. Where this we will call it as, let us say, V2I. This will be V2I will be 12, whereas V2 is, if you see here, this is V2, this is V2I. So both are in reverse polarity only. So V2 equal to minus V2I. So you will get minus 12. Okay, so this will V1 will be 8, V2 will be minus 12 from this. So only thing is, the summary points from this is, I'll consider always second sign, and when I'm even though polarities are different, is like this is given in the problem, like this given in the problem, when you are solving, try to go with your concepts only, so that no confusion. Wherever current entering, there plus, wherever current is leaving, there minus. So this is V2I, like this. So from this circuitry, V1 and V1 equal to 8, V2 equal to minus 12 volts. So V0 and I in the circuit shown in the figure. So this is with the help of KCL. Shall I write like this? This is entering current. This is also entering current. This is leaving current. So minus, or you can write entering currents equal to leaving currents also, but I will follow the basic I naught plus I naught minus 3 equal to 0. But you see here relationship between I naught and V naught is, this is equation 1, this is V naught by 4, this is equation 2. So if you solve the equation 1, how much you got? Plus 0.5 I naught minus 3 equal to 0. So I naught equal to 3 divided by 0.5, which is 6 amps, right? V naught equal to, so from equation 2, V naught equal to 4 I naught 24 volts. So will this is understood? I naught and V naught. So now I am writing KCL here. Will this be fine? Any doubts in this? I'll repeat once again. See, I am applying KCL at node A. So based on KCL, some of the leaving currents I am assuming, some of leaving currents I am assuming, leaving currents equal to 0. Leaving currents equal to 0. But this is 0.5 I naught. This is I naught and this is 3. So but I am considering leaving currents equal to 0, but 0.5 I naught is entering current and 3 amps is also entering current. So I will write with a negative sign minus 0.5 I naught, and this in this branch 4 ohm branch I naught current is flowing. From this branch 3 amps is flowing. As it is entering current, I will assume leaving current as minus, I will write that entering current as minus 3 like this. So this is from based on KCL equation. So if you solve this equation, so 0.5 plus 0.5 I naught minus 3 equal to 0, I naught I will get 6 amps. And see in this branch, if I apply Ohm's law, I will get either this, or you can directly write this also. V naught equal to I naught into 4. I naught into 4. As I naught 6 amps, so V naught equal to 24 volts. Fine. Shall I move on to the next? So can you solve this simultaneously with me, this problem? I want V naught and I for this. So easy way is, now as I have seeing the two loops, instead of applying either KVL or KCL, I will apply easily a nodal analysis. Nodal analysis says you'll combination of Ohm's law plus KCL is the nodal, right? No, right? Nodal analysis. These are all be detailedly discussed in network analysis, but whatever the concepts I need, I'm just considering those concepts. Whatever the concepts I need, I'm just revising that. So nodal equal to KCL plus Ohm's law. The same way, mesh analysis equal to KVL plus Ohm's law. Okay. So generally, if I was solving any equations, applying nodal analysis is easier. So whatever the currents it is showing here, I1, based on the nodal analysis, what it says is, based on the nodal analysis, we'll assume from that particular node all the currents are leaving. All the currents are leaving. So this is, I will assume it as L1, L1, L2, and L3. Fine. What is the relationship between L1 and I1? I1 equal to minus L1. I2 equal to L2. I3 equal to L3. So L1, some of the based on nodal analysis, I will assume that when I am writing the nodal analysis equation, all the currents are leaving from that node. So that's why I'm assuming it as L1 plus L2 plus L3. And this node will have some potential V equal to 0. L1 plus L2 plus L3. All the leaving currents equal to, I am assuming that nodal analysis, all the currents are leaving from that. All the leaving currents, and if I apply KCL, then like this equation you will get L1 plus L2 plus L3. Fine. So now that I will replace with my actual currents. Minus I1 I2 plus I3 equal to 0. Fine. But this is with how you doing it with KCL. But you do with nodal, directly I will write the equation. You see, V minus 5 divided by 2, which will give me the current in this, right? That L1 what I am talking about, right? Same way, plus V by 8 will give me current flowing through this 8 ohm, plus V, because here minus sign is there, V minus of minus plus 3 by 4. Can you solve and tell me what is the, how much you got V?
So V equal to 2 volt.
2 volt.
2 volts or 2 volt.
So V equal to 2 volts. Do all of us has got the 2 volts?
Yes, sir.
Fine. Now what we need to find? You need to find V1, V2, V3. For that to find, if you know I1, I2, I3, it is easy, right? So I1 equal to, how you can find I1? As the current direction is from 5 volts to towards this node. So 5 minus 2 by 2 is I1, right? So this is only just consideration. Now I don't need this. So I want I1 5 minus 2 by 2. That is 3 by 2, 1.5 amps. Same way I2 2 by 8, 1 by 4, that is 0.25 amps. I3 2 plus 3 by 2 plus 3 by 4, 5 by 4, is 1.25. So you just check it out the answers here. So I1 equal to 1.5, I2 equal to 0.25, I3 equal to 1.25. So once you got the I1, I2, I3, it is very easy for you to find out V1, right? How much is the V1? Can you tell me V1? How you will find out V1? Equal to I1 multiplied by 2, right? 1.5 by multiplied by 2, it is 3 volts. Same way V2, I2 multiplied by 8, so I2 is 0.25, 0.25 multiplied by 8, it is 2 volts, right? 0.25 multiplied by 8, 2 volts. In the same way V3 is I3 into 4 ohms. I3 is 1.25 multiplied by 4. V3 is 1.25 multiplied by 4. How much? 5 volts, right? Yeah. Any doubts in this? For this finding all the voltages and currents in the circuitry. Simply I will apply a mesh. You see, only with the help of two equations only you got the entire. Instead of applying separate KCL and again there the distribution. So that's why nodal is easy. Moving on to the next problem. So you can solve this by your road and move to the next problem. Same way how you solve the previous thing. So all this is at one node only, right? All this is at one node. So assume this as a voltage V and apply accordingly. So write the equations and solve. Can you ping me the answer?
V equal to 20, V equal to 20, sir. 20 volt.
20 volt. All of us got 20 volts only. What is the nodal equation for this? V by 4K, right? I will assume all the currents are leaving only. So this current is V by 4K. And this current as entering, but leaving current I will assume. So that becomes minus 10 milli plus V by 5K plus V by 20K. So if you solve this equation, you will get V. So my friend is saying 20 volts.
20 milli.
20 milli.
1 minute, sir.
So now see, V of 1 by 4K. Do with calci.
20
1 by
volt,
5K.
20 volts only, sir.
1 by 20K equal to 10 milli. So milli may cancel each other. Here all K milli. So equal to 20. So if substitute there, that with the help of, if once we got V, then automatically we will be able to get the current in this loop. Once we got the current here, V1 equal to what? The current, if you find out whatever that is, let us say I3K, let us say.
15 volts.
So V1 equal to 15. And same way. And I think you can tell directly V2.
20 volts.
V2 equal to V right here. Equal to 20 volts. So this is the final problem, I guess, in the network analysis to solve. So I'll move on to the analog electronic concepts. So you try to apply. This is the previous gate question. What are the concepts you know till now? Whether I need to apply nodal here, mesh here, KCL here, KVL here. Is asking voltage E. Is asking voltage E. There are so many paths are there, right? This is one path. This is one path. This is one more path. And this is one path. So if this many paths were there, you tell me which path will give you easy answer. Which path will give you easy answer? Path 1 or 2 or 3? Path 4? Path 4 anyhow it is not considered only because it not includes E only, right? So among this, which path you will consider to solve finally? You just see that?
3.
Yeah, obviously, right? If I go for path 1, there are 2 unknowns for there, which is not given in the problem itself. And path 2, there is one unknown, that is V1. It is not given. So we will consider path 3 and We'll try to solve this. And you see this 10 volts means how it is connected, like this, right? Ground, this 10 volts is connected like this. So I'll always start from the my known voltage source. So starting the ground, and obviously 0 volts means it is at ground only, right? So you may looking like this is open, but it is closed only, loop only, right? Starting the ground, and again here 0 volts means that is ground only, right? Reaching the ground, it is loop only. So KVL you can apply. It's not that you can't apply. So always considering second sign, 10 plus 5 plus E plus 1 equal to 0. So E equal to how much? Minus 16 volts. E equal to minus 16 volts. Fine. With this, the summary for this, whatever I need is, so whenever I'm applying KVL, I will always start from the ground and reach the ground, and I will try to take the second sign of that particular voltage. And if any voltage sources were there, we can't change the polarities. But if any passive elements were there, that is resistor, wherever in my loop direction, so this is my loop direction, right? In this loop direction, my current entering, there plus will be there, wherever my current is leaving, there minus will be there. So whatever the asked in the problem, I don't bother. Later I will go with my method. Finally I will try to relate, after finding the values, I will try to relate what is asked in the problem, so that you won't have any confusion. Fine. And next one more is, we will always try to apply nodal analysis in a given circuit, so that it is easy to find out. So if you see, briefly I will explain you the what actually the diode is, how it will operate, and then you will see the diode equivalent circuits. So if you see the diode operation, please pay attention in coming 10 or 10 minutes. So if you see PN junction diode operation, you can see in these three cases. If you try to understand with the help of these three cases, one is unbiased condition, one is forward bias condition, and one is more is reverse bias condition. So there are some more basics has to be known. Can you tell me what are the different currents you see in a semiconductor? What are the different currents you see in the semiconductor? If you remember any, can you name whatever the currents you remember? Yeah. In semiconductor, what are the currents? Yeah.
Drift current.
Yeah, obviously drift current. That's a very good answer, Ashwini. Drift current. If drift current, you know, almost obviously diffusion current.
Diffusion, yeah.
Yeah, diffusion current. And majority carrier current, minority carrier current, and there are so many currents you listen. Reverse saturation current, forward diode forward current, reverse current, like this. So all this, whatever the currents you listened, all this comes under these two categories only. Either it will be diffusion current, that is, diffusion current means free flow of charge carriers from higher concentration to higher concentration. This is higher concentration to lower concentration, higher concentration to lower concentration. That is diffusion current means there is no external force, like if water is falling from the hilly area to the down area like that. Here the concentration of the charge carriers were more, here the concentration of charge carriers is less. There will be free flow, there is no external influence, free flow from higher concentration to lower concentration. Then that current we can call it as a diffusion current. The same way, drift current by a force, by applying some external force, if the charge carrier is moving from here to here, then that current, we are calling it as a drift current. Generally drift current we will see, this is a general case, it's not always drift current will be from lower concentration to higher concentration. That not good. For generally drift will happen like this, from lower concentration to higher concentration. The drift will happen with the help of some external power supply, like you are pumping the, with the help of motor, you are pumping the water to the hilly area, like that. So that is drift current. If external supply is external energy is needed, that is drift current. Under the influence of external energy, if the charge carrier is moving, then that is drift current. And see, what is the current direction you need to consider? If it is whole movement is from left to right, if the whole movement is from left to right, then the contribution of the current because of the whole movement from left to right in the direction of left to right only, that is I whole current. Whereas if the electron is moving from right to left, because of the electron is moving from right to left, the contribution of current because of the electron movement is from right to left is from left to right, opposite. For hole, the resultant current will be in same direction, whereas for electron the resultant current will be in opposite direction of the electron movement. So but if equal to I hole and I electron, that is, this is about diode forward current, that we will see in detail in coming discussions. You see the symbol, anyhow you know the symbol of this. Can you know why this arrow is represented like this? What this arrow indicates? What this arrow indicates?
Direction of current.
Yeah, conventional current direction or direction of current from anode to cathode. And by the symbol we can say that diode is a unidirectional device. And will the diode is unipolar device and bipolar device? So this is unidirectional device. Only the current flow from anode to cathode, whereas cathode to anode there won't be any current will be there. That's why it is unidirectional device. Now tell me, so unipolar, bipolar, I will tell you. If the current which is flowing in that particular element is only because of any one charge carrier, either it is hole or electron, any one only contributing the current, means then that device is unipolar device. Whereas both electrons and holes were contributing in resultant current, then that device is called as bipolar device. So tell me, will the diode will be unipolar or bipolar?
Unipolar, sir.
Unipolar. Any other answers? I'll repeat once again what I told. In a resultant current, let us say diode resultant current is forward current, right? So that forward current is because of electrons or holes or both. Based on you are saying unipolar, it will be both, either any one only the contributors. So we just I will at the end I will answer this. Okay, whether it is unipolar or bipolar, or you only tell me. So and when
So bipolar.
yeah, obviously this is bipolar, that I will conclude when after discussing about it. So the crystal structure of pentavalent elements. Know that periodic table there are groups will be there, right? Fifth group, those are pentavalent elements. So and consider the phosphorus from that fifth group. So if the crystal structure will be the electrons, 4 electrons will be forming the bonding with other phosphorus atoms, but 1 electron is ready to detach from the phosphorus, because any material try to achieve the inert gas structure, that is maintaining the 8 electrons at the outer shell, outer orbit. Outer orbit means valency orbit. So phosphorus is ready to give this electron. In the same way, if you consider the third group elements, which will have 3 electrons in their valency shell, those 3 electrons will be forming a bonding with the other 3 electrons, so that totally it will have 6 electrons, and there will be a vacancy will be there. So this vacancy has to be filled with some other electron, so that it will form a bonding with another electron, so that total 8 electrons will be there. So there will be always vacancy is there. That vacancy of electron, we are calling it as a hole, right? Vacancy of electron, we are calling it as a hole. So trivalent impurities we will represent, because as you know, any material is electrically neutral, saying it will have equal number of protons and electrons. Equal number of protons and electrons will be there. But as the phosphorus is ready to give this electron, so once this electron is lost, number of electrons will be now how many protons will be more, or electrons will be more? If this is lost, if this electron is lost, now positive charge carriers will be more, right? This is electron is negative charge
Yes.
carrier, so positive charge carriers will be more. That's why wherever pentavalent impurities were used, in whichever the material pentavalent impurities were used, the atoms is represented with plus sign with a detached electron. Okay, in the same way, wherever trivalent impurities we will use, as it is taking extra electron, so the number of electrons becomes more, so the atom becomes electrically unneutral. It is positive charge, from positive charge with a vacancy of hole. Okay, like that we will represent. So wherever trivalent impurities if you use, what semiconductor material it will form? If you use trivalent impurities, whether it will form p-type material or n-type material. So p-type means majority or holes. So obviously trivalent impurities I will use in p-type. If I want p-type semiconductor, I will use trivalent impurities. In the same way, if I want n-type material, I will use pentavalent impurities. Okay, till here is understood, right? So based on that only, this representation. Okay, so p-type with a negative ion with the vacancy of electron, that is hole. N-type positive, the atom will becomes positive because it is ready to detach this electron. So now to form a p-n junction diode, you will bring this p-type material and n-type material closer. Once you bring it closer, what will happen? The free flow of charge carriers, because you see in p-type material, which were the majority? Holes were the majority, and you see red color, in this red color, electrons will be minority. In the same way, n-type, you see which were the majority? Electrons were majority, and you see some red color holes were there. So holes were minority in n-type. Fine. Now because you brought the both the p and n type material closer like this, there will be here, you see, in this n type electron concentration is more, whereas in p type electron concentration is less. So the free flow of electrons from here to here, electrons. The same way, free flow of holes from here to here. So when that movement is happening, there will be a recombination at here, forming a immobile ions. As the hole is moving from p side to n side, as here at this atom, electron is there, that hole will recombine with that electron, and this atom becomes immobile. In the same way, the electron from n to p type is moving. The electron is from n to p type is moving. So here at this atom, there will be a vacancy of that electron is there. So the electron will recombine with the hole available here, so that it will forming a negative ion like this. So you see, and now because of the forming ions near the intersection of p and n type material, so near the, this is intersection of p and n type material, right? So this we will call it as a junction. So junction. So at this junction, ions were formed. So as this is positive ion here, so this positive ion, as you know, same charge carriers will repel each other, and the hole is also a positive ion. So as the further movement of the hole is happening from p to n side, this immobile ion will repel that hole movement, so that hole can't able to move. Free movement will be stopped. And the depletion region, the immobile ions were there, that we are calling it as a this width W, we call it as a depletion region width. In the same way as here in p side, negative ions were there, that stops the further movement of electron from n to p. So under the unbiased condition, there will be junction is formed, and the depletion region will be formed. So this is unbiased or open circuited p-n junction diode. Fine. So now you need to give some external energy, so that this barrier will be removed. This barrier will be removed, and the electrons will move further, will freely move again. Fine. So we'll try to make connect that as forward biased and what is the meaning of forward bias? This is anode is connected to the positive of the battery, and cathode is connected to the negative of the battery, then we can call it as a forward bias. So now in this condition, what happens, as you are keep on further and further increasing the external voltage, this will reduces the barrier potential. The external applied voltage will reduce the barrier potential, or other words, you see, this is negative is there, negative terminal is there here, and here holes were there so this negative terminal will attract these holes. So as the concentration is here is increasing, the holes will try to move towards this side. The same way electrons will try to move towards that side. That makes the depletion region lesser. What is the meaning of depletion region? Depleted of charge carriers, there won't be any charge carriers because of this attraction. This in the depletion region also, that charge carriers will be available, so that the depletion region width will be further and further will decrease, so at some particular voltage, this depletion region won't exist, so that again charge carrier moment will be there from here to here. That is majority carrier moment. What about minority carrier moment? As here plus is there, minority carriers here are electrons, right? Electrons will move like this. So in forward bias diode, there will be only majority carrier current will be there. Majority carrier current will be there, and the majority carriers beginning at till some voltage, that is, let us say if it is silicon diode, 0.7. After 0.7 voltage is applied here, so after 0.7 there won't be any barrier potential is there here, so that the charge carrier moment will be there from n to, electron moment is there from n to p, and hole moment is there from p to n. So now tell me, so this IF is bipolar or unipolar? This forward current, that is because of hole moment from here to here, that will give you hole moment, that will give you IP, and electron moment is from here to here, that will give you IN. So both IN and IP are in same direction, that's why these two are added to each other. Okay, IP and IN. So now tell me, this forward current is bipolar current or unipolar current?
Bipolar.
Obviously, right? Both holes and electrons were contributors were there, so this is bipolar. And whether it is drift current or diffusion current, you try to understand. Electrons were more here, electrons are less here, and that until that barrier is broke down, till then only this external supply is needed. Once the barrier is broken, later the movement is free flow. Later the movement is free flow from N to P and P to N. So the forward current is diffusion current. The forward current is diffusion current. You may say that, sir, what about this battery then? Not only I am telling, this external forward bias voltage is only up to some 0.7. If the voltage is crossing that, afterwards it is free flow only. You see the forward bias characteristics. So let us say this is 0.7 till here, very less current. Suddenly the current will shoot up because that barrier was removed, right? And this increment will be parabolic variation. It's not linear variation. It's not like this linear variation. It is a parabolic variation. Clearly understood. Means there won't be any influence of this forward voltage is not there on this majority carrier moment. Okay, any doubts in this? Moving on to the next. So forward current is diffusion current. If you connect the same diode in the reverse bias, what will happen? Reverse bias means anode is connected to negative of the battery, cathode is connected to positive of the battery. Then what happens? As negative is there here in p type, majority carriers are holes, right? All the holes will try to attract towards this side. All the electrons will try to attract to this positive terminal, so that majority carriers won't move from here to here. They will not move. Okay, what are the left out? As the now here you see, now minority carriers in p type are electrons, right? So this electron, minority carrier here, electron here will be attracted by this, so it will try to move from here to here, and you see as you keep on varying this, the depletion region width is further and further is increasing, because the charge carriers moving away from the junction, So the depletion region width is keep on further and further increasing, but this electron is under the influence of, even though here the concentration of electrons were more, under the influence, because of this battery, under the influence of the external battery only, this electron is moving from here to here, that is from lower concentration to higher concentration under the influence of external supply. That's why this is the minority carrier current, and that's why this minority carrier current is called as drift current. Minority carrier current is called as drift current. So anyhow, in the same way, the minority carriers in the n-type is hole will also move towards this side. So minority carrier current IP will be towards this direction, and this is IP minority. The same way, electron is moving from here to here, so IN minority. So reverse saturation current will flow in this direction, that is IS, from cathode to anode. Okay, so reverse saturation current is also a bipolar current, right? Because both the holes and electrons were contributors for that. Okay, so if you use a symbol, the connection mechanism of reverse pass diode is like this. So the IS is the reverse saturation current which is flowing from cathode to anode. So if you see the diode equation, it's just a mathematical equation represented in terms of minority carrier current IS. Minority carrier current IS. I can call this as a Shockley's equations also. William Shockley given this equation. So this equation ID equal to IS. Sorry, Shockley's equation for PET. So this is for a diode. This is diode. ID equal to IS into e power KVD by TK minus 1, where KD is the Boltzmann constant, TK is the temperature in degree Kelvin, where VD is the voltage across the diode, where VD is the voltage across the diode. So this is the utility factor, which is equal to n equal to 1 for germanium, n equal to 2 for silicon. Generally we will use silicon only in our problem, so most probably we will substitute n equal to 2 only in our problems. So that equation only, if you see, what are the main things to be remembered from that equation? E power KVD by TK minus 1, where ID is the diode current or IF, ID or IF, forward current. So you saw, from that equation, try to solve this problem. Silicon diode has IS equal to 10 milliamperes operating at 27 degrees centigrade. Calculate ID for the forward bias regulator of 0.6 volts. So means VD is given here is 0.6. What is the equation you know? ID equal to AS into sorry. Solve this and tell me the answer. substitute substitute in this equation. It is given this is 10 milli k equal to, that is 2, how much we'll get, that value substitute here, it is 11,600 by 2, 5,800. Vd is 0.6 Tk. Temperature in Kelvin, it is given temperature in degree centigrade, 27 plus 273 will give you temperature in
1.09 kiloamps, sir.
how much?
1.09 kiloamps.
Yeah, 1.09 kilo milliamps, right? 1.02 milliamps. ID equal to 1.02 milliamps will get. See, 10 multiplied by 1.02 milliamps. All of us got?
So 1.09 kilo, sir.
Yes, sir.
Kilo. Let me check it out once. Because it is already IS is given milli. Yeah, fine. It has to be micro, but it is given milli, that's why. 1.09 kiloamps. Generally, as you know, IS will be is in the range of microamps. Reverse saturation current will be in the range of microamps, whereas ID is in the milliamps. But here in the problem, IS is given itself is milliamps, so that's why you're getting more current. Okay, a correction here. If you substitute microamps here, then you will get milliamps range. Generally, for a forward bias diode, the forward current will be in the range of milliamps. If you see the diode parameters, some more diode parameters. So forward bias diode will have some resistance and that is forward resistance RF, that is forward bias diode, and the reverse bias diode will have a reverse resistance RR. As you know, forward resistance is in the range of ohms, and reverse resistance is in the range of mega ohms. And this is for diode, general diode, and that this resistance is also further divided into static resistance and dynamic resistance. So static resistance is defined as voltage by current, voltage across the diode by voltage across the current, whereas dynamic resistance you will find change in voltage by change in current. Change in current will give you the dynamic resistance of the diode, and the formula will be RD equal to this is actually RD equal to VT, this is R, VT by ID, where VT equal to thermal equivalent of voltage, that is 26 millivolts. At room temperature, we will consider it as a 27 degrees centigrade. If you consider the room temperature, the thermal voltage will be 26 millivolts. So RD equal to 26 millivolts by ID, where ID is the current flowing through the diode. And knee voltage or cut-in voltage is the forward voltage at which the diode starts conducting. And breakdown voltage, there are two types of breakdown voltage for there. That is, one is avalanche breakdown and Zener breakdown. Avalanche breakdown is generally will see in the lightly doped diode, whereas Zener breakdown will see in the heavily doped diode. But whatever we discussed till now, whatever the operation we seen, is a general diode which is using moderate doping, not high doping. So these two concepts will further will see detail in Zener diode concepts. But there are two types of breakdowns will be possible. And one more thing to be remembered regarding here avalanche breakdown is avalanche breakdown will damages the device. So and the Zener breakdown will be useful. And also Zener breakdown will be happening in lesser reverse voltages, that is less than 5 volts, whereas avalanche breakdown will happen in high voltages. Peak inverse voltage, maximum reverse voltage that can be applied across a PN junction diode without causing any damage to the junction. Peak inverse voltage. This is, remember, peak inverse voltage means maximum reverse voltage you can apply across the diode. So this will help you in selecting the suitable diode for your circuit operation. Maximum forward current, and as the name is self-explanatory, maximum power rating. So now we'll see the diode equivalent circuit models. So when you are solving the problems, which model, which diode equivalent model I has to use so that I can solve the problems easily. There are three types of models are possible. One is ideal model. Ideal model means the VT is the cut-in voltage. Cut-in voltage is 0. Forward resistance is 0. Reverse resistance is infinite. Means if this is the diode symbol, if diode is forward bias, you will replace with the short circuit. If the diode is reverse bias, you will replace with the open circuit. Open circuit means resistance is infinite like this. The same way approximate model we will use. If you are you generally when you are solving any problems, based on the problem we will go and for a practical diode you will have approximate model and you have piecewise linear model. And in approximate model you will solve the cut-in voltage 0.7 or 0.3, So 0.7 for silicon and 0.3 for germanium, and RF is 0 and RR is infinite. So corresponding equivalent circuit will be look like this. Only thing is, if you try to extend here, always cut in voltage will come like this. Whereas the whereas reverse biased approximate model equivalent will be obviously open circuit only. Okay, and whereas piecewise linear model of the diode is cut in voltage will be based on the type of the diode, whether it is silicon or germanium. 0.7 or 0.3 will be replaced, and uh, the forward resistance will be replaced with the help of dynamic resistance of the diode, that is RD, and RR is the infinite. So accordingly, if the forward bias diode, the symbol will be cut in voltage followed by forward resistance and diode. And generally if it is nothing is mentioned in the problems, we won't use this piecewise linear model. That's why I put a cross mark here. So we'll try to always use approximate model only when you're solving the problems. So this will be more helpful for us. So try to remember, these two are needed for us. So now in this problem, find the value of I. So please note, when you're solving the problems, as we seen from the definition, if the diode is forward biased means anode is connected to positive terminal and cathode is connected to negative terminal of the battery, and like that is the definition for the forward biased diode. But when we are solving the problems, we won't see the both the terminals of the diode where it is connected. We will see any one terminal is satisfying the definition of forward bias, then we will say that diode is forward biased. And one more thing is, now in this the diodes were ideal. Assume that diodes were ideal. Each and everything is clearly mentioned in the problem. Accordingly, we will go. Diodes were ideal. Ideal means if the anode is more potential than the cathode, then you can say that diode is forward biased. So, and you just see here, this is diode D1 and diode D2. As diode D1 is connected to negative of terminal of the battery, obviously diode D1 will be reverse biased. The same way, diode D2, anode is connected to positive, obviously it is forward biased. Fine. But if you see the resultant equivalent circuit, this is reverse bias diode is open circuit, replaced with open circuit. Forward bias diode will be replaced with a short circuit like this. Now we need to find out I, right? Means this branch is eliminated only, right? Because of this open is there here, this branch is eliminated only, and you find out I in this loop. So your current direction is like this. So how will write the equation? So this is plus polarity minus polarity. The voltage across here is 10I, right? This loop, and this is plus and minus. I will always consider second sign. So minus 10I minus 10 is equal to 0. Minus 10I minus 10 equal to 0. I equal to minus 1 amp. I equal to minus 1 amp. So tell me the I in this circuitry. Now I want to know whether this diode D1 will be forward biased or not, right? This cathode is connected to minus 20 volts, right? Obviously, diode D1 will be forward biased. Once it is forward biased, replace with the short circuit. Ten ohm, 20 volts. Fine. Simply, obviously, this is minus polarity of this battery, plus polarity of this battery, and current is also entering here. So I equal to
3 amps.
3 amps. I in this 20 ohm resistor here. Because see, this and this and these are parallel branches. The voltage at each that is 10 ohm and 20 ohm will be same, right? So I'm assuming that here diode is ideal. Diode is ideal. Current I is 20 volts by 20 ohm. That is 1 ampere you will get. 20 by 20. If the diode is practical, let us say practical, and cut-in voltage, you just try to see. If you are not understanding, try to apply KVL here. Fine. So if you apply KVL, see here, current is entering at here I plus terminal and minus terminal. I will always consider second sign. Minus 20I plus here second sign plus 20 equal to 0. Okay, I equal to 1 you will get. That is for if it is ideal diode. If it is practical diode, you need to replace with the cut-in voltage and 0.7. I am assuming if it is nothing mentioned, I will always assume the silicon diode it is. Until unless it is not mentioned in the problem that it is germanium diode, I will always assume it is silicon diode only and always replace with the cut-in voltage 0.7. Okay, now the equivalent circuit becomes replace with the cut-in voltage. $20 and this is plus minus P gamma. This is also 20. Now try to apply same concept. Current direction is like this, right? So plus minus 20I minus 0.7 second sign minus 0.7 plus 20 equal to 0. Fine. So minus
0.96.
obviously 0.96. So now you try to understand, right? If it is ideal diode, you will get 1 ampere. Or if it is practical diode, 0.96 you will get. .96 you will get. Means what I am saying is, if it is practical diode and there is no forward resistance of diode is given. So if the forward resistance is not given, then I will assume it is 0 and I will replace with the cut-in voltage only. But in the problems, it all depends on the problem theorem. If in the problems RF is mentioned, so the corresponding equivalent circuit to be diode has to be replaced with the help of like this equivalent circuit, RF followed by 0.7. So I think rarely you will use this, but you just know it's all about the based on the given problem. Okay, so we use this concept mostly until unless RF is not specified. If RF is specified in the problem, we will use this equivalent model. Okay. So find ID and V0 in for this circuitry. So from this equivalent circuitry also I given. Can you tell me now, applying the suitable equations, what are the concepts you know? Solve. Did you got answer for this? Whether the diode is forward biased or not. Here. You see -5 means this can be realized like this, right? So the cathode of the diode is connected to minus of the battery, so obviously diode is forward biased only. Once it's forward biased, replace with the equivalent circuit, that is 0.7. Is in this problem V gamma is given as 0.7. That's why I am you may have a confusion that whether I need to go for ideal model or practical model. So in the problem V gamma is given, so that I am substituting the equation 0.7 with the equivalent circuit 0.7. It is clearly mentioned use ideal diode, you can go with open circuit and short circuit. Even though there they will mention that sometimes use ideal diode, rest of all the characteristics ideal, but only use V gamma equal to 0.7 also they can mention. At the time you need to, it's all according to the given problem. If the given problem is cut-in voltage is given, you need to use it. So if you apply in this loop, always follow the second sign, minus ID multiplied by 22K minus 0.7 plus 5 equal to 0. From this, (4.3) divided by 22K.
(1.95 into 10 power minus 4).
So in the milliamps,
Point.
195 milliamps. Always try to mention the values in some milliamps or microamps given value. The GATE exam they will ask like that only. 0.195 milliamps. So once we got that, then how about V naught? V naught equal to positive or negative value V naught will be. Will the V naught will be positive or negative? You see here in the equivalent circuit. Here V naught we need is like this, but the whatever the value you will get, I naught multiplied by 22k will be polarity will be shown here like this. Obviously V naught will be negative of 22k multiplied by ID. K multiplied by ID.
Minus 4.29.
Yeah, 4.29 volts. Yeah, a few more problems were there. After that, we will wind up today's session, and in next class we will see the rectifiers. So we just see this was the given problem. So given problem, this is equivalent circuit. This diode has to be forward bias or reverse bias. We have to know. See, plus is there, anode is connected. So obviously we'll always go with that diode will be forward biased. So once the diode is forward biased, try to replace with cut-in voltage and apply the equation ID. So this is 8 minus ID into 1.2k minus I2 into 4.7k. Solve simultaneously with me. Minus 0.7 equal to 0. So ID equal to 7.3 divided by 5.9, right? 5.9k. (1.23 milliamps). Do you got the answer? You got the answer? 1.23 milliamps.
So 1 minute.
See, you will get from here idea. Yeah. Same way, once you got ID, this is ID. Once you got ID, you can able to find out easily V naught, right? From this equivalent circuit, V naught. V naught is here. This one. This one. So there are two possible ways to find out V naught, right? One is voltage across is 4.7K and cut-in voltage. Sum of these two voltages will give you V0. And also one more path is there. Is 8 volts and voltage across the 1.2K. That will also give you V0, right? You can find out in two possible ways, but both will get almost near answer. .7 multiplied by 1.23 . So this you will get 6.5. If you find out from here, that you will get 6.48. Almost same answer only, right? Got it? The voltage drop across 4.7K and voltage drop across the diode will give you V0. That is one method. That will with that you will get 6.48 volts, or else you use this loop. This is loop 1, or this loop. This is loop 2. Any one is enough. Same answer only you'll get it. Find out V01 and V02. So as silicon diode will anode is connected to plus of the battery, and also germanium diode plus is connected. So obviously both the diodes will be forward biased only. Once it is forward biased, silicon diode is replaced with a cut-in voltage of 0.7. Germanium diode replaced with a cut-in voltage of. Some of the textbooks will assume the cut-in voltage of germanium diode as 0.2. Some of the textbooks will assume it as 0.3. So it will be clearly mentioned in the problem anyhow. So I will consider for this germanium diode cut-in voltage as 0.2. So this is 12 and 0.7, 4.5K, 0.2. So obviously from this I can say that directly V02 equal to 0.2, as both are 0.2. Now V01, to find out V01, so V01 is at here, right? So V01 means like this, right? So I'll simply apply like this. I want the voltage at here with respect to ground. At V01 means with respect to ground. So this is ground. So starting ground, reaching ground. So here only loop will be there. Second sign always 12 minus 0.7 minus V01 equal to 0. From that V01 equal to 11.3 volts. Understood? V01 equal to 11.3 volts.
Yes, sir.
And this one, last problem. See, as these two are in parallel, so the cut-in voltage of germanium diode is less. So once as these two are parallel branches, across the parallel branch, the voltage will be same. So as once the germanium diode comes into conduction, it won't allow the silicon diode to come into conduction. So the cut-in voltage available across from this, the voltage will be here from here to here in this node is 0.2 volts. So V0 will be 11.8 volts. Because both diodes are connected to plus of the battery, but as these two diodes were in parallel, so silicon diode won't get sufficient cut-in voltage, because the cut-in voltage of this is 0.7. The cut-in voltage of this is 0.2. So once the voltage is keep on increasing, once the germanium diode comes into conduction, it won't allow the silicon diode to conduct. So silicon diode won't comes into conduction. Both are forward biased only, but germanium diode comes into conduction. Silicon diode is forward biased, but not in conduction, because the voltage across here is not crossing 0.7. It is at 0.2 only. So that's why output voltage will be at 11.8 volts. Okay, understood now. Till now we seen only forward bias or reverse bias. Now it is forward biased and in conduction.
Yes, sir.
Okay, so these are the topics I'm just briefly show you what I'm going to discuss in coming class, and then wind up today's class. So rectifiers, detailedly we will discuss about half-wave rectifier, center tap full wave rectifier, bridge full wave rectifier operation. Once that is properly understood, based on that, if till now whatever the problems we see in diode related problems we seen only based on the DC voltages, DC voltage sources, DC voltages. But if his AC voltage is applied, then the equations becomes phasors. So if phasor equations are coming, then how we will get the output equation there? For that to understand, we have to know the mean value, mean square value, root mean square value, all those things. From that, we will try to come up with the final output equations. So we need to detailing has to discuss the rectifiers, and we will solve all these problems, important gate problems, in the next class.
Yes, sir.